G'day, mate. That's Australian for hello. Oh, I crack myself up. You see, that was funny because Australian, not a language. Yeah, they speak English in Australia. Anyway, so hello everyone. Welcome to this video on 10.5, Tangents Part 2, where we will do one new theorem in this section. It's Theorem 10.11, which says, if you have two segments that are both tangent to a circle, and they have this point here in common with each other, then they are going to be the same length as each other. So if AB and BC are both tangent to the circle, then they are congruent. We're going to get to do a proof about this because it's super fun and it makes the theorem make a little bit more sense. So let's take a look at a proof. In this proof, we are trying to prove that the line segment AC will be equal or congruent to the line segment AB. Let's take a look at the information that we're given. So far, all we know is that both of the line segments are tangent to circle H. And of course, they both have the common point A. So if we know that they're tangent, what does that tell us about them? All lines that are tangent to a circle are also what? They also have to be perpendicular to the circle. So we know that AC has to be perpendicular to circle H, and so does AB. It has to be perpendicular to the radius. So this is going to be this radius here, and it has to be perpendicular. Same thing with the other one. Because it's tangent, we automatically know it's perpendicular. Watch what I'm going to do next. I'm going to add an extra line right here in the middle. And now we have two triangles. We have two right triangles. So if we're trying to prove that AC is congruent to AB, I could prove that the triangles are congruent to each other. And if the two triangles are congruent to each other, then eventually I could use CPCTC, which says the corresponding parts of congruent triangles are congruent. So my new goal is actually to prove that the triangle on the top is congruent to the triangle on the bottom. Once I prove that those two triangles are congruent, then I can use CPCTC and prove that segment AC is congruent to segment AB. So what do I need to do in order to prove that the triangles are congruent? Well, to prove triangles are congruent, we're going to either use side, 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 side angle, side, one of those to prove that the triangles are congruent. So let's take a look at the information that we already have about the triangles. Okay, first off, we already know that angle C and angle B are congruent because they're both right angles, and we know that they're both right angles because there was a theorem that says if a line is tangent to a circle, then it's going to be perpendicular. So to start off with, I'm going to say angle C and angle B are both 90 degrees because there was a theorem that said that if a line is tangent to a circle, then it's going to be perpendicular to the radius of the circle. And since they're both 90 degrees, that means that they're equal to each other, of course, because they're both 90 degrees. You could also like use substitution and stuff, but we're just going to say they're both 90, so therefore they're equal. So we already have one equal thing. We have that angle C is equal to angle B. They're both congruent. What else do we know? What about HC and HB? Those are congruent. How do we know that? They're both radius. There was another theorem that said all radii in a circle are congruent. So therefore, HC is congruent to HB. All right, what else do we know? HA is congruent to itself because of the reflexive property. So let's see what we have. We have an angle, we have a side, we have another side. Ooh, I remember that's not one of the ones we can use. We cannot use angle side side. Remember, that was the bad one. Can't use that. So we got to come up with something else. What else do we know? Okay, I just looked it up. Here's how we can finish this bad boy off. So we actually don't really need to use CP/CTC for this one. We can actually prove that segment AB is congruent to segment AC. There technically was a shortcut in one of the chapters, I think we skipped it, for right triangles to prove that right triangles are congruent, but that's okay, we don't need the shortcut. To prove that AB is congruent to AC, notice in a right triangle, we have the a squared plus b squared equals c squared Pythagorean theorem. So if we already know that the a's are congruent, and if we already know that the c is congruent, doesn't that automatically mean that the b is going to be congruent as well? It does. That was actually one of the shortcuts that we kind of skipped over. So because these are the third sides in a right triangle, we can automatically know that they're going to be congruent to each other. There was a shortcut theorem, something called like hypotenuse leg. In a right triangle, once you know the hypotenuse and one of the legs are congruent, then you can tell that the third side is going to be congruent. So according to that shortcut theorem, because this is a right triangle, we can say that side AB is congruent to side AC because of the theorem hypotenuse leg. Or we can also just say because it is the third side of a right triangle when you already know that one of the legs and the hypotenuse is congruent and you know it's a right triangle. So therefore, those sides are congruent. So we have proved this theorem. Now we get to use this theorem to solve problems. Here's the first one. AB and CB are tangent. Our theorem said if they're tangent, then they are equal. So x plus 15 equals 2x minus 5. Now we solve for x. Subtract x, add 5 to both sides, and x is 20. Here's one for you to try. Actually, there's two of them for you to try. Go ahead and pause the video, give these two problems a try, then you can check your answer. All right, so these are the two answers. Go ahead and skip the next 30 seconds of the video if you got them correct. If not, keep watching and I'll explain how to get these answers. All right, so in both of these problems, we have some tangent lines here, and we know that the tangent lines are going to be congruent because our theorem said that. So 3x plus 8 is equal to 26. So 3x is equal to 18. So x is equal to 6. And now for this next one, we have 2x plus 9 equals 3x plus 6. Now we can solve it by subtracting 2x on both sides, and you can subtract 6, so we get that 3 is equal to x. And the last thing for today is not a new theorem, but it is a new vocab word. A circumscribed polygon is a polygon that is outside of a circle. So the polygon would be like the triangle here in the first picture, or this quadrilateral here, or this hexagon here. Those are all polygons that are circumscribed. So there's a circle inside of them, and notice that it touches at all tangent points. These are examples of polygons that are not circumscribed. The important thing to note here is that if a polygon is circumscribed, it touches it at tangent points, which is important because everything we're doing in this section is all about tangents. So this problem here is one that we can solve because we know that it is circumscribed, which means that it touches it at tangent points. So this is a point of tangency, this is a point of tangency, and this is a point of tangency, and that allows us to solve this problem here. So this problem says a graphic designer is giving directions to create a larger version of the triangular logo shown. If triangle ABC is circumscribed about G, find the perimeter of ABC, perimeter. So we need to figure out what this distance here is. I'm going to label this with an X. We need to figure out what this distance is. We need to label this with a Y. And then once we know that, we can add it all together because perimeter is all the outside. So we already know 10, We already know 8, we just need to figure out this little bit. And we already know 7, we just got to figure out this. Then we can add it all together for the perimeter. How do I find x and how do I find y? What theorem have we been using today? The theorem says if you have a point outside of the circle, like this point here, C, and if it is tangent to the circle at these 2 points, our theorem says that these lines are congruent. We're going to use that theorem from today in order to solve the problem. Let's start here with this point A. This point A, if we draw a line to D, the line segment AD is tangent, and line segment AE is tangent, and our theorem said these are equivalent. So x is equal to 8. How do we find out what y is? Take a look at the bottom of the triangle here. In the bottom of the triangle, the whole thing is 10, and this part from F to B is how long? It's going to be 7 because EB is 7, and they're going to be congruent. So if the whole thing is 10 and if that part is 7, it means that this little yellow part is 3, which means that y is also 3. So just using the theorem from today, we were able to solve for those missing pieces. So to find the perimeter, we're going to add it all together. 8 plus 3 is 11. That's one of the sides of the triangle. 8 plus 7 is 15. That's another side of the triangle. And then 10 is the other side of the triangle. So adding it all up, we get the perimeter of the triangle is 36. I'm going to ask you guys to try one problem like this on your own, and that's going to be the last one that we do today. Go ahead and pause the video here, give this problem a try, and once you're done with this problem, then you are done with the video. Here's the answer. Go ahead and check your work, and if you would like to hear an explanation, keep watching because I'm going to explain how to get the answer. If you don't need an explanation, then you're done. You can submit this onto Canvas and have a great rest of your day. All right, in this one they tell us the perimeter is 18 and we're trying to find out what x is. So let's zoom into this picture here and start writing down some things that we know about this. Well, I know that if AT is x, then TB also has to be x. Also, if UC is x, then BU also has to be x. And if AS is 3, then SD has to be 3. Same thing with this side, it also has to be 3. And they said the perimeter was 18. So let's see, I have 4 x's total, plus I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and the perimeter is 18. So now we can solve this and we can find what x is. We can subtract 12 from both sides, and then x is going to be 1.5. All right, guys, that's it. Great job today, great work. Go ahead and submit those notes onto Canvas, and that's it. You're done with the video. Bye.